Okay, let's take a look here at second order partial derivatives. So we're taking the second derivative, but of partial derivatives. Well, here we have the different partial derivatives that we can take. So we can take, well, our first order derivatives are the partial with respect to x and the partial with respect to y. And then we can say, well, how does our first derivative with respect to x change as x changing? And we can also think about how my first derivative with respect to x changes as y changes. Similarly, we can take the partial with respect to y and see how that partial is changing as y changes. And we can think about how the y partial changes as x changes. So we have 4 different second order partial derivatives, and let's look at how you'd calculate them. So first thing that you do is let's find the first order. So f partial x is going to be y squared plus 6x e to the y. And then we can say, well, how is that changing as x changes? That's going to be 6 e to the y. Similarly, how does f partial x change as y changes? That's going to be 2y plus 6x e to the y. So we just took the derivative of that with respect to y. So these are my first two. Now we say, okay, my partial derivative with respect to y is 2xy plus 3x squared e to the y. And now we need to take the partial of y and see how does my partial of y change as y changes. So as y changes, how is my first order differential partial derivative changing? That's going to be 2x plus 3x squared e to the y. And my partial with y, as x changes, we get 2y plus 6x e to the y. Now, while this is just our first example of looking at this, it's important to draw attention to the fact that these are the same value. And later on we'll show that they in fact always are. All right, let's look at sort of a raw crunching way of figuring out a second order partial derivative. So we've got here a table of x values and y values. And first we want to find the partial of x at the point 1, 2. So at the point 1, 2, we're right here. If we want to find f partial with respect to x, we're saying as we change x, as x goes from 1 to 1.1, where we fix y, so keep y at 2, and let's change x. What happens is our z value goes up 1.6 from our x values changing by 0.1. So this is my change in z over change in x. So this predicts that for every change in x, our z value changes by 16. What about my f partial at the point 1, comma 2.2? So we go down to the point 1, comma 2.2. We say, okay, if I change my x value, my y value goes up by 2.23 when x changes by 0.1. So that's a change of 22.3. So notice that my, and these are rough approximations for my partial derivative with respect to x at 2 points that are close to each other. And so what we can do is we can say, well, as y is changing, as our y value went from 2 to 2.2, what we saw is an increase in my partial derivative with respect to x. Therefore, we can say my second order partial derivative, which is saying how f of x is, sorry, how f partial of x is changing as y changes at the point 1, 2. Well, my change in f partial x over my change in y, when my y went down by, or sorry, when my y went up by 0.2, my partial derivative with respect to x went up by 6.3. So this equals 31.5, which says that as y changes around this point, so around the point 1 comma 2, so at 1 comma 2, a slight change in y, so a change in y results in my partial derivative with respect to x to increase. Or to be more clearly, at the point 1, 2, an increase of 1 in the y direction would result in an increase of 31.5 in my partial derivative with respect to x. Okay, as I said before, there's an important theorem, and we showed it in the first example, but the theorem states that f partial xy is equal to f partial yx at some given point. And just to be clear what those means, f partial xy is saying, how does my partial derivative with respect to x change as y is changing at a given point? And f partial yx is saying, how is my partial derivative with respect to y changing as x changes at a given point? All right, well, why do we care about this? What do the second order partial derivatives tell us? Well, for one, if we think about single variable calculus, when the second derivative is greater than 0, we know that our function is concave up. Similarly, when it's less than 0, our function is concave down. And when it changes sign, or when it's equals 0 and then changes sign, we have a point of inflection. We're going to show similar things there. So, for example, if f partial xy is less than 0, this means that my derivative, my partial derivative with respect to x, so my partial derivative with respect to x is decreasing as y increases. So that means that as y is getting bigger and bigger and bigger, our derivative in the x direction is getting smaller and smaller and smaller, or more and more negative. Well, how else can we use second derivatives? We can use second derivatives to do Taylor approximations of curves. Now, if we remember from single variable calculus, in BC single variable calculus, we looked at Taylor approximations. And the whole idea of Taylor approximations is that let's suppose that you have some curve. The easiest way that we can think about a curve is, well, we can think about that curve as being a straight line. But that's not a great approximation. So other than a straight line, we could say, well, we could do a second order differential equation. Sorry, a second order Taylor approximation. And if we do a second order Taylor approximation, instead of doing a linear approximation, we're going to do a quadratic. So that would look something like this. And now that becomes even more accurate. So here we have a reminder from single variable calculus, which is a Taylor polynomial of degree 2 approximating f of x. The analogous equation for Taylor polynomials of degree 2 approximating f of xy is as follows. And this is around the point 0, 0. So notice we've got what z equals at 0, 0 times the first partial derivative with respect to x at 0, 0 times x plus the partial at y with 0, 0 times y. And this constitutes a degree 1 Taylor polynomial. And this looks familiar. This is just the equation that we have that we've used before already for a plane. But now to make it even more accurate so that it's not just a plane, but we're creating a degree 2 equation, we add in our second derivative with respect to x times x squared plus f of x, sorry, f partial xy times xy plus f partial yy times y squared. And notice that this is divided by 2 and this is divided by 2, but this one is not, and this one's not because it's repeated twice. Because you had the f of xy and f partial yx. And they're the same thing, so they added together to just be 1. Because each one of those was over 2 factorial, which you remember from Taylor approximations. Okay, well let's look at an example of how that works. So here we've got a function f x y, and we want to find the Taylor approximation. So the first thing that we need to do is find all the partial derivatives. So we know that f partial x is going to be negative sine of 2x plus y times 2 plus 3 cosine of x plus y. And f partial y equals negative sine of 2x plus y plus 3 cosine of x plus y. And if we plug in the point 0, 0, we're going to get negative sine of 0, which is 0, plus 3 cos of 0 is just 3. And similarly, if we plug 0, 0 into f partial y, we're also going to get 3. So my linear approximation will equal f of 0, 0. So if I plug 0, 0 into this function, I'm going to get 1 plus 3x plus 3y. Now we need to find, and that's given right here. Now we need to find our second order. So to do that, we're going to need to find more partial derivatives. So we get f partial xy, which equals negative cos of 2x plus y times 2 plus 3 sine of x plus y. And when I plug 0, 0 into this, we're going to get negative 2. And this also equals f partial y x. Okay, then we need f partial x, which will equal negative 4 cosine of 2x plus y plus 3 cos of x plus y. And if we plug 0, 0, 0, 0 into this, we're going to get negative 4. And f of f partial y is negative cosine 2x plus y plus, or rather minus, sorry, and this should have been minus sine. So minus 3 times sine of x plus y. And again, plugging 0, 0 into this, we get negative 1. So then our equation becomes q of xy equals our point at 0, 0. So we know that f of 0, 0, same as last one, it's just 1. So we have 1 plus 3x plus 3y plus negative 4 over 2x squared plus minus 2xy. So the minus 2 is coming from f partial xy. And lastly, minus 1y squared over 2. So we're just filling in our partials into our Taylor, second order Taylor approximation. So just to kind of give a little sense, let's imagine that we have some function here, and our linear approximation would be to take every one of these curves and make them into a straight line. Whereas our quadratic approximation takes every one of these curves and turns them into a quadratic. So you see you have part of a quadratic there. This is going to continue to make one. So the more approximations, so the higher order Taylor approximation, the more accurate it will be. So just kind of going back to what we just did, what we did is we found the both the first and the second order Taylor approximations of this curve. Now, just as a reminder, what we in single variable calculus, we're able to represent sine of x as a Taylor approximation right here as follows, which the yellow highlighted part is our second order approximations, since we want a quadratic approximation. So given that we knew this already, or knew this at one point, we can then pretty quickly write this equation as a second order Taylor approximation by filling it into this equation. So this will equal qx of y will equal the approximation of sine of x plus y, which is just plugging in that into our x value, so x plus y, plus, so that is our sine approximation, plus 1 minus 2x plus y squared over 2. And that is our cosine second order approximation, which is right here. And if we went ahead and expanded this, we'd get x plus y plus 1 minus 2x squared minus 2xy minus 1/2 y squared. And this should look pretty familiar because this is what we redeveloped right over here. It's exactly the same thing. So it might be worth going back and doing some review of our single variable Taylor approximations. I did realize, however, that missing a major detail, which that this in the example had been a 3, which makes this 3x plus 3y. And so now it looks exactly as it did before. Okay, so this is just looking at how we can write cosine of 2x plus y in a Taylor approximation, and the highlighted part is our quadratic. Similarly, here's sine of x plus y written in our Taylor approximation, and the highlighted part is our second order differential, or our second order Taylor approximation. So here's the general equation. We saw it before, but you may want to pause this video and just write this down in your notes. The difference between this and what we looked at, however, though, is that this equation for our second order Taylor polynomial is that it's no longer surrounded or around the point 0, 0, but now we're talking about being centered at the point a, b. So now we have a, b, x minus a, y minus b. Here, x minus a, y minus b, x minus a squared, y minus b squared. So we just need to center our Taylor polynomial. We have to center it around the point in which we're concerned. Let's look at an example of that. So let's say that we've got the point or the function. Let's just think of a really easy one. Let's say, like, I think this is easy, x squared y cubed, and we want to center it around the point 1, 2. So we know that f of 1, 2 equals 8, and f partial x is the following, and that equals 16. And f partial y is as follows, and that equals 12. F partial x x, 2y cubed also equals 16, f partial xy, we get 6xy squared, get 24. And lastly, f partial yy is 6x squared y, which equals 12. So therefore, my second degree Taylor approximation at the point 1, 2 is going to equal 8 plus 16x minus 1 plus 12y minus 2 plus 16 over 2 x minus 1 squared plus 24 times x minus 1 y minus 2 plus 12 over 2 times y minus 2 squared. Okay, so now just to practice, find all 4 second derivatives. Let's just do one of them. We'll do number 2. So f partial x, chain rule, just drop the 2 down. F partial y, same thing. And I think it's helpful sometimes to distribute. So the second partial derivative with respect to x we get is 2. With respect to y, also 2. And f partial xy equals f partial yx, which is, once again, 2. That was kind of a boring problem, I guess, all same answers. Okay, so now we're going to find a Taylor polynomial of degree 2. Let's choose this point. We're doing it around what point? Let's choose a point to approximate it around. Let's just do it around the point 1, well, maybe 2 comma 1 or 1 comma 2. Let's do it around the point 1 comma 2. So we know that, so let's do just 12. We know that f of 1 comma 2 equals, plugging these points in, will equal 4. Now we have to find the partial derivative, so f partial x is 2 y minus 1 x plus 1. And evaluating it at that given point, we also get a value 4. F partial y will be as follows, and this again equals 4. Okay, now we need to take the second order partial derivatives. So f partial xx, this is just a constant, so we're times the derivative of this function, it's just going to be 2y minus 1. And when we plug in our point, 1, 2, we're talking about a value of 2. And f partial yy, well, there's no y values here. So as y changes, this is just a constant. So this equals 0. And f partial xy, what we're looking at is how this changes as y changes. So 2 is a constant, x plus 1 is a constant. The derivative of y minus 1 is just 1. So this ends up being 2 times x plus 1. And if we plug in our point, we get 4. So now we just fill in our second order Taylor approximation, Q for quadratic, equals, we'll plug in the point 1 comma 2. Our function equals 4. So we have 4 plus our first derivative with respect to x. So 4 times x minus 1 plus our partial with respect to y, 4 times y minus 1 plus our second order f partial xx. So that's plus 2 over 2 x minus 1 squared. And I made a mistake. This should have been y minus 2. 2 because it's the point 2. And I know that I said about 0, 0, but I'm doing this about 1, 2. Okay, so then we have plus. Now we've done this, this, this. I'm going to skip the FYY and go right to here. So that's plus 4 times x minus 1 times y minus 2. And then lastly, plus f partial y. Well, that's just 0, so plus 0. And there's my quadratic approximation for the function y minus 1 times x plus 1 squared, centered at the point 1 comma 2. Okay, the last problem that we're going to look at, we're doing because it introduces an important equation. It's called Laplace's equation, and Laplace's equation states that the second partial in x plus the second partial in y will always be 0. And we'll look at this a couple times over the course of the next couple days to investigate what this means. But for right now, let's just do a problem which confirms this. So if we take our partial with respect to x, we get negative e to the negative x sine y. And if we do that again, because e to the x doesn't really change except for that negative, we're going to get, it's going to be positive again. So e to the negative x times sine of y. Well, now looking at partials with respect to y, our first one is going to be e to the negative x cosine of y, and then the derivative of that with respect to y is e to the negative x sine of y, but negative sine of y. So let's put the negative sign out in front. So therefore, when we add those two together, we get e to the negative x sine of y minus e to the negative x sine of y, and we see that this is in fact 0. So again, this problem is more just to do one last review of second order partial derivatives and introduce an equation that we're going to be looking at over the next couple days, which is called Laplace's equation, which states the following here. All right, that's it.